Welcome to A-level physics, looking at nuclear energy. First, we'll start with mass defect. Get two protons and measure their mass. Now get two neutrons and find their mass too. Tip: be careful where you put the protons whilst doing this. They're very easy to put down and lose. Now very quickly and with all the violence you can manage, smack them together. If you do it right, you will end up with a nucleus of helium, two protons and two neutrons. Now weigh the result, and you should find that it's less than the mass of the four ingredients put together. Some of the mass has gone missing. Where is it? Well, did you notice the blinding flash of light and the enormous heat when you smack the four together? That's a bit of a clue as to where the mass has gone. The missing mass has been converted into pure energy. You need to think of energy and mass as the same thing. Mass is just a solid form of energy. So you can convert one to another and back, without breaking the principle of conservation of energy. Einstein wrote the equation that allows you to find out how much energy will be released when you change mass into energy. It is E equals mc squared, where E is the energy released in joules, m is the mass defect in kilograms, c is the speed of light in meters per second. M is the mass that goes missing, the mass defect. It is not the total mass involved in the reaction. So let's work out the mass defect for a helium nucleus. The mass of a proton is 1.6726486 times 10 to the minus 27 kilograms, and the mass of a neutron is 1.6749544 times 10 to the minus 27 kilograms. A helium nucleus has two of each, so the total mass involved for the particles needed to build it are 6.695206 times 10 to the minus 7 kilograms. The actual mass of a helium nucleus is actually 6.64477 times 10 to the minus 27 kilograms. Notice how it is slightly less than expected. The mass defect for a helium nucleus is 5.0436 times 10 to the minus 29 kilograms. Using Einstein's equation, E equals mc squared, this corresponds to an energy equivalent of 4.53924 times 10 to the minus 12 joules. This is quite a small amount of energy in the everyday world, but on an atomic scale it is significant. The numbers are very small and hence difficult to deal with. Physicists often use atomic mass units to deal with the small masses, and electron volts to deal with the small energies. The atomic mass unit, U, is equal to 1.6 times 10 to the minus 27 kilograms, and the electron volt, EV, is equal to 1.6 times 10 to the minus 19 joules. In these units, you should be able to show that the mass defect for helium is around 0.03 U, and this corresponds to an energy of around 28 million electron volts, or 28 mega electron volts. M is mega, i.e. 1 million. The numbers are much easier to work with in this form. Make sure that you can express numbers like this. We're now going to look at binding energy. When you make a nucleus from its constituent parts, you give out energy or lose mass. That means that to break up a nucleus, you will need to put back in the same amount of energy you took out, to convert back into mass. The energy is called the binding energy of the nucleus, as it is the energy involved in binding the nucleus together. Obviously, the bigger the nucleus you make, the more energy you get out. Every time you add another proton or neutron, you get more mass going missing. So the bigger nuclei have bigger mass defects. But if you took out the binding energy per neutron involved in the nucleus, you notice that certain atoms have higher values than others. This is interesting as it suggests that some nuclei are more stable than others. To find the binding energy per neutron, simply find the energy of the entire nucleus and divide it by the number of neutrons, protons and neutrons. It's that easy. If we imagine the original proton and neutrons separated, then energy is lost as we assemble the nucleus. Remember the flash of light? We say that the protons and neutrons have zero energy when separated, and therefore as energy is lost in assembling them, the binding energy per neutron is negative. We can put the same amount of energy back into break the nucleus apart again, and thus we return the original zero energy situation. We are now going to look at fusion and fission. Because iron is the most stable nucleus, it makes sense, in energy terms, for other nuclei to try to become more like iron. So smaller nuclei will combine and give out energy in doing so, to produce larger nuclei, more like iron. This process is called nuclear fusion. Larger nuclei will split up to produce smaller nuclei, more like iron, and give out energy in doing so. This is called nuclear fission. In 1939, physicists realised that energy released during fission could lead to a possibility of a nuclear bomb. The process of fission, I will demonstrate soon. Usually a neutron collides with a large nucleus, setting it into a series of violent vibrations. The deformation caused by these vibrations allows the electrical repulsion between two protons to overcome the short-range nuclear forces that hold the nucleus together. The result is a splitting of the nucleus into small nuclear fragments, and possibly the ejection of neutrons. So a neutron comes in and gives the nucleus a whack, and the nucleus splits into two, and possibly ejects another neutron. These ejected neutrons are often absorbed by non-fissionable material. The nuclear reactions then stop. If, on the other hand, the neutrons are allowed to strike other fissionable nuclei, further fissions can occur. If a situation occurs in which each fission produces, on average, one neutron, which causes one other fission, and so on, we have a self-sustaining reaction. This is called a critical mass. If more than one fission-inducing neutron on average is released, the result is an avalanche of nuclear reactions. This is called a chain reaction. This is a very dangerous situation, deliberately manufactured in nuclear bombs. Nuclear power stations are designed to control the nuclear processes to produce useful energy. The key to controlling nuclear reactions is to produce just the right number of neutrons to cause a self-sustaining reaction, but not an uncontrollable chain reaction. The first problem to overcome is that most of the neutrons produced during nuclear fission move too quickly to induce fissions in other nuclei. Imagine the neutrons zipping through and not having time to start the nuclei vibrating. The neutrons can be slowed by using a moderator. The neutrons produced collide with the nuclei of the moderator substance and lose some of their energy without being absorbed. Then they pass back towards the fuel, where they are more likely to produce fissions with sustainable nuclei. These lower energy neutrons are called thermal neutrons. Graphite and water are commonly used as moderators. The second problem is controlling the number of thermal neutrons. The number of thermal neutrons, and hence the rate of nuclear reactions, must be finely adjusted to control rods. This ensures a chain reaction cannot occur, but a self-sustaining reaction is allowed. The control rods act like neutron sponges. They absorb more and more neutrons, the lower they go into the reactor. These are rods made from cadmium or boron, and can be dropped into a nuclei reactor to shut down the reactions completely if a dangerous situation develops. The most common type of nuclear reactor is the pressurized water reactor, like this one. This design uses water as a moderator and as a coolant. The water is kept at high pressures to stop it boiling, even at 320 centigrade, and driven by powerful pumps to boiler, where it has produced steam to drive turbines and produce electrical energy. Apart from the obvious danger of chain reaction, nuclear reactions also produce high levels of radiation and radioactive byproducts. Safety is a very important consideration in the nuclear industry. Reactors must be properly shielded to stop emissions, and waste must be disposed of carefully for the safety of workers and the public alike. Despite these problems, nuclear power is considered by many to be a clean and relatively cheap form of energy. In addition, it will allow us to conserve our supplies of fossil fuels. It is also a fact that some of the byproducts of nuclear reactions include man-made nuclides that are useful in fields such as medicine and technology. The debate for and against nuclear power is likely to go well on into the future.